Hi everyone, I'm excited to be back with another lecture. So why I'm super excited today is we will talk about a new architecture in this course. So we will talk about convolutional neural networks, which are, I would say, one of the most popular architectures in deep learning because they allow us to do pretty cool things related to image recognition and all other computer vision related tasks. So they are also, for example, powering the technologies behind self-driving cars and other things. But since convolutional networks are such a big topic and there's such a huge amount of research behind it, I decided to split the lecture into two parts. Actually, I wanted to talk about three parts first, where the third part was on face recognition, which is some of my specialties. However, because we also want to cover other topics in this course, I think two parts are plenty. So today we will only talk about the basics. So we'll introduce why convolutional networks are potentially good and how they can improve upon traditional approaches and what the main ideas behind convolutions are. And then I will also show you some examples in PyTorch. And then with that, I think we are pretty well covered for the first lecture to get a feeling of what convolutions are, how convolutional neural networks work. And then in the next lecture, in part 2, I will give you an overview of the most common convolutional neural network architectures. So some of them are still state-of-the-art. They let you produce state-of-the-art results. And then I will also show you how you can use them in your projects. So there will be some code where I will also show you how you can use a convolutional network that has been trained on millions of data points, and you can then adopt it to your own, let's say, smaller data set for your class projects. So with that, let me get started with the introduction to convolutional neural networks, and let's go from there. As always, the lecture material for this lecture will be available on GitHub under this link. And today we will only cover one part of the convolutional neural networks lecture because, like I said, there will be a lot of material to cover because it's such an exciting and well-researched topic. So why do we care about CNNs for image classification? So CNNs is just short for convolutional neural networks, and saying convolutional neural networks every time will take away maybe 10 or 15 minutes of this whole lecture if I have to say it over and over again. So let's just call it CNN for short, which is the common abbreviation that you will also find in papers. So why do you care about CNNs? So maybe you have a lot of cats and dogs at home, right? Like everyone. And sometimes it's hard to tell dogs apart from cats. So maybe you're at home and you have all your cats running around with your dogs, and then you have a hard time telling them apart. So that is maybe one situation where CNNs can be useful. Of course, I was just kidding. So CNNs are in general an method for more efficient image classification compared to multi-layer perceptrons. So there are certain advantages of CNNs that we will look at today that make them better for image data. So that could be, for example, here an image of a cat and an image of a dog. And assuming I have a large data set of a lot of examples from these two classes, I can train a convolutional neural network to classify them. Of course, this is just a very simple example where I only have two classes, and usually this is an arbitrary number of classes, similar to what you've learned before with multi-layer perceptrons. You can have an arbitrary number of classes. And also what's typical is for convolutional neural networks, or CNNs, is they're usually drawn in these rectangular shapes. So if you draw a convolutional network, you will usually see in papers they are drawn like that. So there will be basically a 2D input passed through the network. So in contrast to multi-layer perceptrons, where we had like these vectors for each layer, we now have more like these 2D shapes, and we will go into much more detail about that. So here, the only interesting part is basically that we have images as input, and the CNN can, for example, do a classification here, for example, predicting whether it's a cat or dog. It's nothing new. It's basically the same thing you've seen before with a multi-layer perceptron, except that we have a different architecture that is just better with images. Another interesting application of convolutional neural networks is object detection, for example. So this is a very popular algorithm called YOLO. You only look once. So this is usually called YOLO. There are many other methods for object detection. In this class, we will not talk about object detection because it's a whole topic by itself. However, it's not too complicated, and that would be another, for example, use case of CNNs. somewhat related to object detection, but not quite. It's also its own topic, really is object segmentation. And that would be another really useful area where CNNs can be used. For example, here the mask RCNN. So this is a method for detecting objects, but then also segmenting the objects from the background, for example. Another area that I worked on in the past in several projects is face recognition. So in face recognition, that is also related to CNN. So you can, so this would be a Siamese network. So Siamese networks are networks. It sounds fancier than it really is, where you have the same network copied. So this network is exactly the same as this network. So imagine these are neural networks. This is another neural network, but they are actually the same. So you share all the weights between them, and you pass an input to each, or you pass the input at each iteration to the first network and then to the equivalent same network below here with a different input. And what this network will learn, it will learn a similarity or distance score. So you can train it to distinguish between pairs of images. There are more extended methods, for example, something called the triplet loss, which relies on 3 outputs that are pairwise compared to each other. So, but this is more like the very generic, simple setup where you have 2 inputs and you want to, for example, say whether 2 people are the same or different. For example, if I have 2 pictures of the same person, the network should return a small distance score or a high similarity score. And if this would be a different person, it should give us a high distance and a low similarity, for example. But this is also something I wanted to cover in a part 3. But since we have so many other more exciting topics to talk about, I think I will also skip the face recognition part and just focus on convolutional neural network, which are the foundation of everything that relies on CNNs. So today what I want to talk about is image classification itself, so the task of classifying images, because that's the most fundamental thing you can do with CNNs. So why this is interesting and what the current challenges are with image classification. Then I will talk about the basics of the CNN architecture. So I will show you how this works exactly, because it's not so, I mean, there are multiple parts that have to be combined to make a CNN work well. And then I will talk a little bit about different types of CNN architectures, but only very briefly to give you an idea of how different all these architectures are, because there are many different kinds, and the state of the art, what is the best CNN architecture, constantly changes. So there are many papers I think there's probably one new CNN paper at least every week or month with a new architecture. So then I will also briefly talk about what a CNN can see. So like talking about techniques for introspection, where you can take a look at what the network learns in the intermediate layers, so what it is really doing. So CNNs are essentially feature extractors. So they extract features from the images, and we also can take a look at these features, so to kind of understand a little bit of what it is really looking at. And this is just part of the model evaluation. It's not super important, but super interesting. And then lastly, I will show you how you can implement CNNs in PyTorch. And this is also, thanks to PyTorch, pretty straightforward, but it's worth talking about. So these were topics I had in mind for today. And next lecture we will talk about some more, I would say, advanced topics, padding. So today I won't talk about padding. If you don't know what it is, don't worry about it for now. Some techniques we have seen before, but now for convolutional networks, such as dropout 2D and batch norm. Then some notes about CNNs on the GPU, because there's also a slight difference compared to running them in the CPU, and there are some challenges I will talk about, but also only very briefly, because the focus of next lecture will be the CNN architectures in more detail. So I mentioned there are several architectures, and here I'm only mentioning them very briefly, and then next lecture we will talk about them in much more detail. And then also a very interesting topic related usually to CNNs is transfer learning. Transfer learning is a very general method. It just means that we can use a pre-trained model and fine-tune it to a new data set. So usually this is very useful if we have only a very small data set that is not big enough to learn a good neural network. But with transfer learning, we can load a pre-trained model that has been trained on millions of data points, usually image data sets. And I think this is just a good point to introduce transfer learning because it may be very useful for your class project. So why is image classification so hard? So one of the reasons is that the same image can come in a different variety of forms. For example, with different lighting conditions, different contrast and viewpoints. And that can be a problem for a classifier. So for example, most of the time we think of a classifier as something that takes weighted inputs as input and then performs some transformation to these inputs. And then if it exceeds a certain threshold, then we assign a certain class to an input and otherwise a different class. So for example, in the very simple case of logistic regression, we have the weighted inputs plus a bias. So this is our net input, and then we apply a sigmoid unit, and we say if this output is greater than 0.5, then it's, let's say, it's dog, and otherwise it's cat, just for example. Say approximately the same concept applies also to multi-layer perceptrons, but we have more layers, so there's more complexity to it. But essentially, there's a weighting of some inputs. And now what happens is, or if you think about it, if I have an image that has relatively dark pixels, and the pixels are usually between 0 and 255 in an RGB color space for each channel, and the brighter the pixel, the higher the value in each color channel. So we have 3 color channels from where the values can be between 0 and 255. And now let's say I make all the pixels brighter, for example, then it may be, if we assume that all weights are positive, it would be easier to exceed this threshold here, right, at 0.5, because now I make everything brighter. So for example, if my net input was before my sigmoid activation was before, for this one, let's say it was 0.4, it may now be 0.8, assuming all the weights are positive if I made everything twice as bright. So that might be a problem for our model, because now we haven't really changed anything about the geometry of the image. It's still the same object, but it fails to make a correct prediction just because we changed some intensity values. Similarly, for example, skewing the image moves pixels around, still the same object. For a human, easy to tell that this is still a cat, but for a computer it may be more challenged. Computer may be more challenged because pixels are missing now in this region where we had pixels here before. And similarly, if we translate pixels to different positions, for example here this 5, totally different pixel values will be on in the input, because in the previous methods what we did is we concatenated each row so that we got this very long vector. And in this image, for example, the pixels are more in the early layers. So, for example, in the early positions. So for this one, it is more like in the first third of this vector, and for this one it will be somewhere in the back here. So this way we kind of have different positions where the pixels end up if we have this vector representation, and this makes it very challenging for the methods we have seen so far to generalize from training examples that are not very preprocessed. So most of the traditional approaches kind of use what I would call hand-engineered features. So if we think back of our iris flower example that we talked about in the very beginning of this course, this would be an example where someone manually extracted features to help machine learning algorithms. So for example, iris flowers, for example, look like this. So that would be an image of an iris flower. But instead of having a data set of these flowers, of these images, what people did is they took measurements. So for example, here they measured the sepal length, sepal width, petal length, petal width, all in centimeters. So for one flower, they had like these measurements as for values, and they were fed then into the machine learning algorithm. But this, of course, requires domain knowledge, because for different problems, different properties are important. And you have to be somewhat familiar with flowers to know that there is a difference between, or the leaf size is important between these different classes, for example. So you have to have some knowledge about it. And of course, it's a lot of work to do these measurements. You also have to make sure that you measure the flowers approximately when they are the same age, because otherwise, if you measure baby flowers and old flowers, you get also very different values. So you have to be somewhat of an expert to do that. And it's, of course, a lot of work. It's not feasible to do that for millions of flowers. So with CNNs, we hope to basically perform operations on raw data, for example, the images, directly. So another example of hand-engineered features is, for example, in face recognition, where traditional methods relied on so-called facial key point detection. For example, to predict whether two photographs are of the same person, people would extract these facial key points and then compare the geometry of two sets of key points to see whether that's the same person or not. It's also one more traditional way of doing certain things. Or another relatively, I would say, common approach is to pre-process an image. And this is also to some extent still important for CNNs. And pre-processing usually includes something like background removal, recentering objects that we care about, resizing. So for example, taking this cat, removing the background and moving it to the center, and then doing that for all data points in the input data set, in the training set. Of course, this is also a lot of work. There are algorithms that can automatically remove the background, but it's never fail-safe. I tried this a lot of times. It's a lot of false positive, I would say. So there are a lot of garbage is produced by this if you don't check it manually. So it's also a lot of work even to just remove background and crop these images. And then also, if you train a model on such a data set, it's maybe easier to train, you get higher performance. But then when you want to use your model in the real world, it's usually not so clean. You don't have data that looks so nice. So you would have to also apply your pre-processing pipeline to every input data point that you have. And that is also one challenge. And so people try to develop methods where you don't need this, where you can provide the input image as it is, and then do or get a good performance on the original image. So that was just very briefly one of the challenges in image classification, that we have images of a variety of forms, backgrounds, everything that can distract from the main object, and it can be a problem for traditional machine learning algorithms. And with CNNs, we want to see an improvement over that, or we want to develop methods that are more agnostic to certain fluctuations in the data, in image data. CNNs and what makes them so successful in practice. There are three key ideas behind CNNs. There's sparse connectivity, parameter sharing, and the fact that modern CNN architectures have many layers. So sparse connectivity essentially means that for a single unit in a hidden layer, this unit is only connected to a very small number of units in the next layer. So if you think back of a multi-layer perceptron, we had, let's say, this is one layer or one hidden layer, and this is another. We had every value or every unit in this hidden layer connected to every other unit in the next hidden layer. So everything was fully connected. This is why we call them fully connected layers also. So in convolutional networks, this is different. There's only, one unit is only connected to a small number of units in the next layer. There's also parameter sharing, which means that we only have a smaller number of parameters, and we apply these parameters to many different regions in the image. And then also we reuse that concept in the hidden layers. This is something we will see in a moment. And the fact that there are certain tricks that allow us to have many layers in a deep neural network, convolutional neural network, also helps us with the performance, because you can think of a a CNN as a network that can extract complex pattern from the data. And the deeper we go, the more I would say, abstract these features can become. So in the early layers, CNNs usually learn very small, precise features that can be found in the input image, and then the further or deeper we go, these little patterns assemble to a global pattern. That is also a very powerful concept behind CNNs. Let me show you one of the early CNN architectures. So as far as I know, this is the first CNN that has ever been written up or presented in a paper. So this is by Jan LeCun and co-workers from 1989. And usually this is still a kind of concept that still is often applied. The first part of a CNN consists of convolutional layers, and they're usually for feature extraction. And instead of manual feature extraction, which I briefly discussed in the beginning of this lecture, this is more like an automatic one. So the network learns how to extract useful features that are then fed to a classifier unit, which is more like a multi-layer perceptron. It has these fully connected layers. So since this figure is not super nice to look at, here's one that is maybe easier to talk about. It's the same concept, just a little bit newer paper. So again, we have these parts where we have automatic feature extractor and a regular classifier, and we have in between these convolutional layers, and we have subsampling layers, and what this is I will cover in a second. And then here are the fully connected layers. I don't want to spend too much time on one figure or on all the concepts in one figure. We'll go through them one at a time. One thing I want to mention first is these parts here. These are our main convolutional layers. And so the convolution layers are not these things themselves, but these are the outputs after applying a convolution. The convolution is the operation that maps a region of pixels from an input to a pixel in the so-called feature map. So this is also called a feature map. And here we have 1, 2, 3, 4, 5, 6 feature maps. So this is what this number means. There are 6 feature maps after applying the first convolution operation. So the input is 32 by 32, 32 pixels wide and 32 pixels high. And after applying the convolution, the output feature map will be 28 by 28, so it's a little bit smaller. And we have now 6 of them. And then there's another operation which is called subsampling. And usually subsampling is used to reduce the size by half. So here what happens is we have this here the same number of feature maps. So we also call the feature maps channels. We have also 6. However, you can see now that these are 14 by 14, so they're exactly half as before. And then after this convolution and the subsampling, we have now smaller feature maps, and then we apply the same concept again. So we again have a convolution and another subsampling. So here we have 2 convolutions and 2 subsamplings, and then we have feature maps, 16 feature maps. Each feature map is 5 by 5, and then we will reshape that to a vector 120. And then apply fully connected layers to it. So this part is essentially like a multi-layer perceptron, where the inputs are 120 values. And you can think of them as feature extracted from this original image. So again, so you can think of all of this block as a feature extraction engine, and then the last part is the classifier that classifies what, for example, letter this is. Yeah, so the feature detectors here, so they are also sometimes called filter, and these are essentially weight matrices that slide over the input image. So we'll show you some more figures about that. So usually you start in the upper left corner. This is so it's the same filter. Then you compute the first value here, and then you slide it over to the right. So for example, you This may not great. You slide it over to the right by a little bit, and then you compute the second pixel, and then you slide the same thing over to the right again, and so forth. And you do this for the whole image. So you have this sliding window that goes from left to right here, and then does the same thing. So you apply this sliding window. So then you get these pixels here. And yeah, this is the convolution operation, and there are parameters involved. For the subsampling, there are no parameters. This is usually selecting a maximum value in a certain region, or it's averaging. And I will show you in detail how that looks like also later in this lecture. And this is usually called pooling. And yeah, this is also where the parameter sharing happens for the convolutions, because when we slide the weight matrix basically over the input image, we use the same weights. So that is where the parameter sharing comes from, and also the sparse connection, because each unit here is only connected to a small region here. Well, this region is essentially only connected to this part here. So there's this sparse connection in that way. In this particular paper, they used Gaussian, they call it Gaussian connections, which are essentially fully connected layers with a mean squared error loss. However, nowadays also, it's beneficial to use softmax and cross entropy if we do classification. So in fact, most modern CNNs are using softmax and cross entropy in the last layers. So let's zoom in into one of these convolutional operations. So what we have here is a so-called feature detector. In this case, it's a 3x3 feature detector. In software documentation, you will also often see the term filter, and personally I often refer to it as kernel, which is more, I would say, a little bit traditional term. So the term feature detector, filter, kernel all mean the same thing. And this is something that slides over the input image. So, but for a second, let's focus on one individual step. So when we apply this kernel to an image region, the image region is also a 3x3 region if the kernel is a 3x3 kernel, and this is called the receptive field. And what the kernel essentially does, it's computing a weighted sum of these pixels in the receptive field. It's a very simple operation. It's just weighting these pixels and then summing them up, and then this creates one value in the feature map. So the idea is that in this weight sharing concept is that if this part learns to extract some useful information from the image, then this is likely also useful in other regions of that image. So we keep reusing that. It also leads then to the sparse connectivity, that only each pixel is only connected to a small patch of input pixels instead of being fully connected. And this is really helping also with training neural networks very efficiently. So, and of course also it's a nice reduction in the number of parameters. So what it also does, it's keeping the number of parameters small, because right now we are just reusing the same 3x3 weight matrix for the whole image. So that means we only have 9 parameters. So there will also be a bias unit. So in that case, there's always a bias also added to this. So in that case, we would actually have 10 parameters for this operation, which is actually super nice because it's much smaller than in a fully connected network. So for example, if this is a 28 by 28 image, in the case of MNIST, we had a weight matrix that was 784 times whatever the size of the next layer was, which can be pretty large. So how that looks like then, that sliding, I try to animate this here in the presentation slide software. So what it does, it's basically sliding from left to right, and then it starts in the next row. So we go over this whole image basically. So this will compute the values in the feature map. So this is creating just one feature map. In the previous figure, the one from the paper, you've seen there can be multiple feature maps. In order to create multiple feature maps, we simply have to use multiple kernels. So if we want to create 3 feature maps, we have 3 kernels. So here we, the in black, this is the first kernel. I should also keep the same color. In black, this first kernel. Blue is the second kernel. And red is the third kernel. And this is exactly the same concept as before. We just slide these kernels over the input image to produce the feature maps. So in this case, if we have 3 kernels, we would have 9 features. So 9 features because of the one kernel has a 3x3 is a 3x3 matrix, then times 3, right? Because we have 3 kernels now, plus a bias unit for each kernel. So we have 3 bias units. So in that case, we have 30 parameters. So this is again the 3x3 kernel. We have 3 kernels and then 3 biases or bias units. Yeah, and this is how the convolutional operation works. So it's simply a kernel sliding over this image and then computing the input in the next layer. That is the feature map. So what is the size of the feature map? So there's a simple equation that we can use to compute the size of the feature map. So what I mean is when we go from this part to this part, what is the size? So what is the height and what is the width? So what we can do is simply, oops, it was a bit too far. Apply this formula. So it gives us the output width. We can, if the image is symmetric, if it's the same height and width, then we can use the same inputs here. So this is the width, input width. But of course, you can also replace this by the height if the height is a different number. Otherwise, you can use the same value here for height and width if it's a quadratic image. So what we do is then we simply subtract the kernel width. So again, if we talk about height, you can also replace this by the kernel height. And then we add padding to it. We have not talked about padding here yet. And that is what we will talk about next lecture, because I, again, want to keep this lecture to 1 hour and 15 minutes. I don't want to cram too many things into this one lecture, so I don't have to go too fast. So next time we will talk more about padding. For now, you can assume padding is 0. So this is a 0 term. And then we divide by the stride. Stride is also something we have not really talked about yet. Stride here simply means how many pixels we move it to the left or to the right. So before, what I showed you here is, oops, we had a stride of 1, right? So we were moving it by 1 column, 1 pixel column. So this would be a stride of 1. We can also move by 2 columns instead of 1. Then it would be a stride of 2. So stride means how many pixels we move it to the right. If it's 1 pixel or 2 pixels or 3 pixels. So in our case, we had a stride of 1 because we were only moving it over by 1 position. Again, is another example. So to better understand the number of parameters and the relationship to the kernel dimensions. So here I'm just showing you an image from MNIST. So that is a 28 by 28 image. But independent of the image size, we initialize the kernel. So the kernel is not depending on the image size. So this actually doesn't play any role in the size of the kernel. Kernel is completely independent because we can choose it based on how we like. So the only requirement is that the kernel is smaller than the image, or at least has the same size. So in this case, I'm setting up a kernel, a 5x5 kernel, stride 1. So it strides over or slides over the image by 1 pixel at a time, so 1 pixel position. The number of input channels is 1 because this is a grayscale image. So we have 1 color channel, 1 times 28 times 28. And the number of output channels I choose, let's say, is 8. So it will create 8 feature maps. And then I can, similar to our fully connected layers, look at the weight matrix and the bias. So you can see here, if I call weight.size, the size is indeed 8 for the number of channels, the number of output channels, times 5 times 5, and 1 because we have only 1 input channel. So there will be, I will show you later an example with color channels where this is not 1. So this is equal to the number of input channels. And the bias, we have 1 bias for each output channel. So we have 8 bias units. So again, here we would have 8 times 1 times 5 times 5 plus 8 parameters. So one question for you, what do you think is the output size of this image? So if I apply my convolution operation and then create the feature map, what is the size of this feature map? This may be a good practice to use the equation I've shown you in the previous slide. But probably still worth mentioning is that the convolution is actually not a convolution, it's a cross-correlation. So the convolution in deep neural networks is technically a cross-correlation. So these two are related, cross-correlation and convolution, but there's a minor difference which I wanted to briefly cover. It's not super important here, but just to be technically correct and so there's no confusion, let's briefly talk about it. So usually I refer to the operation that computes the feature map pixel from applying the kernel to the receptive field. I call that usually a dot product, but it's not technically a dot product. But if you think about it, if this is a 3x3 kernel, I can write it as follows. Let's say I equals 1 to 9, and then I can just weight the inputs at this position with each weight. And I can also write this as W transpose X if I reshaped the receptive field in the kernel into two vectors. So this would then compute the net input here in my feature map from this one. And so this is not technically correct because we don't do any reshaping in the cross-correlation computation. The formal way to write down the cross-correlation would be this. So where we have two sums, one is over the rows and one is over the columns when we compute this value. So when we start in the center, basically we have two sums, one goes over the rows and one over the columns. And in practice not we, but some people use this symbol here for cross-correlation, that it can be often found in lectures or in textbooks or papers. But sometimes also you will find people use this symbol. It really depends. So officially for cross-correlation, it's this symbol. So usually though in deep learning, because cross-correlation is convolution, we use this symbol. But it doesn't really matter. Usually when you see the symbol, there's a context that says what that means. So for the cross-correlation, if this is my center point, 0, 0, so these are coordinate systems. Let's say this is a coordinate system that has the center 0, 0, and then goes to -1, 1, and 1, 1. If I would apply this equation here with these two sums, how I would perform this computation using the kernel and the activation. So the activation here is the input, so the activation of the previous hidden layer, or also if this is the image, it would be our X. What would happen is in the cross-correlation, we would compute it in this order. So going from here to here. Oops. So I actually wrote it down here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the order when we would go over the sums starting at the negative index and then add a number to it from here to here, from -k to k, where k is the kernel size. So this is how we would compute that cross-correlation, and the difference with convolution is simply that we switch this plus to a minus, and then instead of going like from the upper left corner, we start at the lower right corner, so it's all just rotated, so we go this way. So it's the same concept, the same computation, it's just that the feature map, or not the feature map, but the activation of the previous layer is rotated, or you can also think of it as the kernel being rotated. So in practice, this doesn't really make a difference in deep learning whether we use convolution or cross-correlation, because we could just, if we want to have the convolution, we can just rotate the weight matrix, for example. We don't do that because it's not really necessary. It's just the same computation. But now you know why or where the term comes from. In practice, in other fields, there are some advantages of using the real convolution over the cross-correlation though. And one is this nice associative property here. So this is one advantage in certain contexts why using the real convolution is more useful than, let's say, cross-correlation. But again, in deep learning, it's not super important. Usually most software libraries like PyTorch and TensorFlow, they also implement the normal convolution. So, with normal convolution here, I mean convolution as it is defined in deep learning. So not the real one, but the one where we start in the upper left corner and then go like this. So this is the deep learn. Let's call this the deep learning convolution. But doesn't really matter. And yes, so maybe also it's just a joke, but maybe why the term convolution is more popular for CNNs, or why it's not cross-correlation, is that maybe cross-correlational neural network wouldn't sound so nice as a convolutional neural network, but yeah. Okay, so backpropagation in CNNs. This is very similar to using the multivariable chain rule in multi-layer perceptrons. However, here we have the multivariable chain rule due to the fact that we have the weight sharing. So, but again, we have multiple paths in the network that we have to connect together when we compute derivatives. So here I have a very simple toy network with one input, a weight that is shared. So W1 is the same weight, and it goes on to two paths, compute A1 and to compute A2, which are then combined to compute the output. And then we compute a loss based on a true label and the output here. And this is just a toy network. So this is not really a convolutional network or a multi-layer perceptron, I'm just illustrating things here. So when we are interested in computing, of course, the derivative of the loss with respect to the weight, we only have one weight, weight 1, because this is what we want to update, the weight. So in order to do that, we have two paths here. We have an upper path and a lower path. So when we compute the derivative, we start with this part. So we compute the derivative of the loss with respect to the output here. And then we compute the derivative with respect of the output with respect to A1. And then A1, the derivative of A1 with respect to W1, which is the upper path. I should have used purple for this. So it matches this purple path here. And so this is also, again, what we've seen many times. This is just applying the chain rule here. And then we do the same thing for the lower path here in blue. And we compute again all the derivative, the partial derivatives. And again, we have this W1 term, and we add them together because there are now two paths. We use the multivariable chain rule to compute the derivative of the loss with respect to W1. So, and how that would look like for for a convolutional network is super simple. So where this comes into play is that we have the same kernel at different positions in the image. So if we have this, what I write here as W1, and I have this W2, so this is the first weight in this kernel, these are essentially the same. So they are shared. So I could have also written W1. So this is the same weight that is applied in multiple locations. And again, similar to what I've shown you in the previous slide, which was a simplification of that, we compute, if we compute the derivative of the loss with respect to this W1, we have to basically simply sum up this W1 plus W2, where W1 and W2 is the same, is shared. But again here, when we compute the, if we would expand this using the chain rule, we would see these are actually not the same, because what differs is here, this A1 and this is A2. So these terms are different. But again, it's the same concept as on the previous slide. We sum them up. And optionally, sometimes people also average over these. So if you have used this weight, let's say 30 times here in this image, you would have a 1 over 30, for example. So there's also an optional averaging going on. But yeah, this is all there is to it, to backpropagation in CNNs. Just, I mean, the overall concept, how we compute that, and how this is computed, of course, also depends on how we compute the activation, what activation functions we use, and so forth. But yeah, this is the backpropagation for CNNs. Okay, now that we are familiar with the basic convolutional operation that we use in CNNs, let's move on to the next aspect. So the convolution operation alone does not help us with making the CNNs invariant to scale, rotation, and translation. So for example, to see why we have not achieved translation invariance yet with a regular convolution is that depending on where the objects are oriented in the image, we get still different outputs. For example, imagine we have this kernel at this position. Let me use a different color here. At this position, we would get the input in the feature map at this position. However, so at this position, there are essentially no pixel values. So there's no object in this position. So here we wouldn't get an output for this object. So if the pixel values are all 0 at this position, so this would be also 0 then. So now imagine I would move the 5 here, which I have done in this part here. So now what happens is, of course, that we get the activation here, and in the previous location there's no activation. So in that way, we don't really have achieved this invariance to translation, scale, and rotation yet. So that means our CNN is still sensitive to where exactly the object is oriented. So I can tell you right away, no matter what we do, CNNs are not perfect with that, but there's at least some trick that we can do that this problem can be minimized. So one common trick is using these pooling layers between convolutional layers. So with these pooling layers, we summarize information. So let me go back here. So what it means is basically we apply a regular convolution here, and then we have a pooling layer that summarizes what we have in the feature map. And the summarizing is as follows. We have these, so imagine this is a region in my feature map. So this is the feature, this whole thing is the feature map after applying the convolution. So this is a feature map after applying the convolution. And what we do here is we apply here a max pooling filter. And the filter here is 3x3 max pooling filter. And what it does, it's just looking for the largest value in this receptive field, and in this case it's this 8, so the 8 gets put into the next feature map, and then we slide it over. So this has a slide 3 here, so we slide it over by 3 pixels. So with pooling, it's often common to use the same stride as the pooling size, so there's no overlap. So in convolutions, we usually slide it, for a convolution we would slide it like this. We would have the first convolution here, second convolution here, if we have a stride 1, and so forth. For pooling, we usually don't have any overlaps, so we choose a stride such that there are no overlaps. So with this one will be put here, and then for this part, there's actually a tie. It doesn't really matter, we still pick the largest number, which is 6, and here we pick 3. So this is how max pooling works. And with that information summarization, you can see it doesn't really matter that much anymore where the largest value is located. So for example, if this 8 here, whether it's here, doesn't really matter, it still gets summarized the same position here. So if I go back to this slide, we still can't achieve such a huge invariance to this big difference here between these two numbers. But if we apply a lot of layers and a lot of pooling layers in between, we can get a little bit more scale invariance or translation invariance, because if we have another one, for example, so if we have a pooling layer, it would summarize in this region. And then in the next layer, let's say the pixel would be here. And then we summarize the next time. And the more we summarize, the more invariant it will become to the exact location of this object. Because exactly to this, because of this effect, that it doesn't really matter so much where this number is located in this window here. Also, newer architectures, some of them, they don't use pooling anymore. So you can also achieve a very similar effect by just using more convolutions and then using convolutions with a stride 2. But this is something we will talk about in part 2 when we talk more about particular architectures. So pooling traditionally has really helped with making convolutional networks perform better. But I would still recommend that you perform some image processing. So if you can do some image processing, that's usually always beneficial, especially if you have a small training data set. Yeah, one more thing I should highlight because it's often forgotten. The pooling layers themselves, they don't have any parameters, right? So there's nothing we can learn here. So this is just a max operation where we just pick the largest value, and there's no weight parameter, nothing to learn. So they are also very cheap, basically, these pooling layers. Let's see some more CNN architectures. Next lecture, like I said, we will talk more about them in detail. Here, I would just want to give you a taste of what the more common CNN architectures look like. So after the first CNNs were published in the early 90s, one of the really influential ones, and maybe the most influential ones after the original, was the so-called AlexNet. So why AlexNet was so popular was because in the ImageNet competition in 2012, it really outperformed all the other methods by a huge amount, exactly halving the error rate of all the other methods at that time. And back then, traditional computer vision was still very popular, and this was the breakthrough where people saw in the traditional communities that deep learning is really useful for working with images. So in order to make that possible, there was another really kind of modern approach. It was using GPUs. Back then it was not very common yet to use GPUs for deep learning, and that was also a big achievement in that paper because GPUs played a very important role to make this possible, because the competition was on a very large data set, and for computers in 2012 this was a really big network with a lot of parameters to tune, so using GPUs was also really important to make this possible. So they actually used some more tricks here to do certain things in parallel in the GPU, so which is why there are two things going on. We can just ignore this part. So and this is how, so the lower part, this is how the network looks like. It's a convolutional network with 5 convolutional layers and 3 fully connected layers. So the first convolution layer has a 11 by 11 kernel. The second one has a 5 by 5 kernel. Then we have a 3 by 3 kernel, 3 by 3 kernel, 3 by 3 kernel. And also you can see they are connected with max pooling. So the max pooling layers are not shown. So these are, or the max pooling will happen here in between. So you apply the convolution and then you use the max pooling to get the feature map. They're not showing all individual steps. In either case, we have these 5 convolution layers and 3 pooling layers here shown. And then we have 3 fully connected layers. Here it's called dense, but dense really means fully connected, which are the layers that we used in the multi-layer perceptron. So in PyTorch we call them an n.linear. I will maybe make a implementation of AlexNet and add it to the repository for next lecture. So here are 2 more figures from that paper. So on the left-hand side, they are showing the weight matrices, so how the kernels look like. So what you can see are these kind of interesting shapes, and they look like, if you have ever taken a computer vision class, they look like traditional feature detectors in computer vision, which is kind of interesting at that time. So in that, they showed that the network learns something that people would design by hand. So back then, people designed these filters by hand, and this network learned something very similar, which was very interesting at that time. And on the right side are some results of the classification problem. So as you can see, let me zoom in here. The images are higher resolution than MNIST for sure. So they are 224 times 224. And you can see it's much higher resolution, so it's much more challenging. I mean, this is a lot of parameters, especially if we have 3 color channels like here. So we have to multiply this number by 3. I think it's about more than 100,000 pixels. And what we can see here are different classes. And it looks maybe something it looks like something you have not seen before, how you evaluate this classification result. So here, these are the true labels. And then we have a range of predictions here under each image. So the challenge is with these images now is that there's not only one object in each image. So especially if we, for example, look at this image, there are two things. There's a dog, a Dalmatian, and there are cherries. So cherries are also fruit, so you can also say it's a kind of fruit, and this is a Dalmatian, or I can also say dog. If I say dog, it's not incorrect. If I say Dalmatian, it's also not incorrect. If I say cherry, it's also correct. So there are multiple correct predictions here, depending on what you want to focus on. However, the true label only has one value here, so it's a little bit tricky. If the network predicts Dalmatian, it's not wrong, right? But although the true label was cherry. So how they evaluate it here is, let's start at the left corner. This is a MITE, and they look at the top 5 predictions of the network, the predictions with the highest confidence, the highest class membership probabilities. So they pick the 5 highest probabilities for the 5 highest ranked classes, which are these ones, and they just check whether the true label is inside here. So, and this method is also called top 5 accuracy. So this way of evaluating it. So for the second one, the true label is containership. And again, containership is among the top 5 predictions, but there are also other things like lifeboat, fireboat, drilling platform. Drilling platform is clearly wrong, but yeah, they the most confident one, so the one with the largest bar here, is containership. So yeah, so that is how they evaluated the network, or all the different methods, and this network was able to achieve half the error rate of all traditional methods, which was pretty exciting at that time. Yeah, so here are just some more notes about the number of parameters. So I'm actually not sure if these are the full resolution images, or I think they look more like the full resolution images. Now that I see that, I have it here on my small iPad, but I think if you would zoom in and see that on a large screen, it would still be a high resolution. So I think this is larger than 224 times 224. So what they did is actually they downsampled it to 256 times 256, and then they took random crops that are size 224 times 224. And again, like we talked about in previous lectures, this random cropping also helps a little bit with the invariance, or basically with helping with avoiding overfitting by generating some augmented images so that the network cannot exactly memorize images. So there are many more common architectures out there. So AlexNet is 2012. This is really out of date nowadays. So there were many more in the recent years. So there's some interesting paper. It's already also 4 years old, which is also really old. But interestingly, in the recent years, there have not been that many new architectures. Of course, there are also new architectures that are not in this paper here, but the number of new architectures is decreasing, but then the number of tricks how to make these architectures work better is increasing. So here, these I would say are still very common and popular architectures. And what this shows here is the top 1 accuracy for different networks. So in the last slide, I showed you the top 5 accuracy, which is actually, I think it's a little bit better than top 1 accuracy if you evaluate something on ImageNet. But in either way, so what is interesting here is the comparison between these networks. So how they rank relatively to each other. And this on the left side is just showing us the accuracy in total for the different networks. On the right hand side, this is a little bit more interesting. It also shows the network size, so how many parameters that is. So the diameter of each circle, so here's the legend, is showing us how many parameters it has, the network. So you can see AlexNet should be somewhere in here. Yep, you can see it here. So there's AlexNet. I would say it has maybe about 65 million parameters and has about 55% accuracy. So this is was back then a pretty good network, but of course there are better networks. So one other simple network, this is a very simple architecture, VGG16. It's bigger. It's maybe almost, I would say maybe 130 million parameters. However, so it's also getting a better performance. So you can say maybe, you can hypothesize maybe a bigger network means better performance. So this network has 16 layers, whereas this AlexNet, as we've seen before, has only 5 layers. But this is not universally true. You can see there are many networks that are small, yet they still achieve a good performance. And in the next lecture, we will talk more about these methods in detail. For example, VGG16, inception networks, ResNets, and the network-in-network. GoogleNet is an early version of inception. So we will talk more about these in detail and how they are different. So because they are not just about adding more layers, there are certain tricks added to them. So like I said, there are maybe some networks missing here in this plot because this is from 2016. So there are other common architectures nowadays like DenseNet, MobileNet, and many others that are very useful. But again, this is still, I think, a very good selection to start with, especially for an introductory course. We have not really talked about color channels yet, and the networks I just showed you, they were applied to color images. So far, we only worked with very simple datasets like MNIST. So how can we incorporate color channels now in our convolutional setup? It's actually pretty straightforward. So if we have an input image, for example, here, with 3 input channels, so that these are the RGB channels, we have 3 inputs here, right? So we usually write this as a tensor, but you can also think of it as a stack of matrices. And then for each matrix in the stack, we also have a layer or channel in the kernel. So now instead of having a M by M kernel, we have a M times M times C kernel, C in. This is the number of input channels. And we compute the convolution now. So we compute the pixel in the next feature map by, let's say, first using this first matrix in the stack, apply the convolution to this one, to the first in the input stack. Then we use the second matrix in the kernel and use the second, so we apply the convolution to the second matrix in the input stack. And then we do it one more time. Let me use yellow. We use the third matrix in the kernel stack, and then we apply it to the third matrix in the input stack. Once we've done that, we just sum them up so that the summing is over these 3 convolution applications. So we apply the convolution 3 times and then sum it up. So what we get is one, should we use a different color? We get as output 1 feature map. So if I want to have multiple feature maps as shown here, again, like before, I have to use multiple kernels. So here I'm just using 5 kernels, so I will get 5 feature maps. So this would be kernel 1, kernel 2, kernel 3, kernel 4, kernel 5, and here I also have feature map 1, 2, 3, 4, 5. So in that way, it's the same concept as before, except now our kernel is a 3-dimensional kernel that has multiple channels, but it's the same convolutional operation as before. What's only new is that we then apply each layer in this stack, in this kernel, to each input and then just sum them up. So one note here, this is maybe a bit not ideal. So here I'm saying the input image has dimensionality n1 times n2 times cin, where cin is the number of color channels, if this is an image. However, this is a very common form. This is the NWHC, where N stands for the number of examples, W stands for the width, H stands for the height, and C stands for the number of channels of the image. We have seen or talked about this before. However, PyTorch, for example, and CUDA, they use the other representation where we have the color channel first, so the color channel would be in front here. But it doesn't really matter that much in a conceptual explanation, so just a side note here. Yeah, I'm unfortunately running low on time, and I promised you to keep the lecture at 1 hour and 15 minutes. So let us not waste much time and go through this section rather quickly. I mean, this is interesting, but not super important. I won't ask about this in the exam. So what can a CNN see? So in that, the question is basically, what does a CNN look at in an input image? So in classical computer vision, people designed certain edge detectors, they call them edge detectors, or certain filters that can extract certain properties from images. So this would be a vertical edge detector. And what it does is, given an input image like this, if I apply it to this filter via convolution to this edge detector, what I will get is this output here. And you can see where there has been an edge here, so transition from to, like, say, dark to bright. You can see it put this bar here, so it detected that there's some edge here in this input image. So this would be the vertical edge detector. And CNNs can learn something like this. So if I apply this vertical edge detector to an image, here it's the MNIST image, I can see, for example, that where I have my vertical edges, that it would, for example, here put this color here. So it kind of learns how to extract these edges. And also here there are even parts missing because there is no vertical edge, right? There's only horizontal region. So, and similarly, I can also apply a horizontal edge detector. And CNNs, they kind of learn something like that. So again, these are manually designed edge detectors, and CNNs, they can learn what they want to use as filter, because we use backpropagation and we want to minimize the loss. So with that, we can find the filters that are good for extracting features that lead to a low loss or good accuracy in classification. There was an interesting paper, or there are many papers, but this was one of the early interesting ones, where people looked at what a CNN can see in the different layers. So this is a little bit small, so they are just showing 5 layers here. I think this was maybe LXNet, but to be honest, I forgot. I have to double check. This may have been LXNet. So they looked at the properties that the network learns in the different layers. Here I'm just zooming in a little bit. And what is interesting is that in the early layers, the network learns very rough shapes. For example, here. So here there's even something like these diagonal edge detectors, if you want. So it learns very low geometric things in the images to extract these. And the farther we go, the deeper we go, the more complex the shapes become. So here in the third layer, you can already see that it learns more to regard the whole image rather than just detecting smaller edges. And the further you go, for example, here the dogs, the more abstract, so the more complex these shapes become. So in the early layers, there are usually more simple shapes that the network detects, and then later it assembles them to more complex shapes. Okay, the last part is CNNs in PyTorch. PyTorch is such a nice library. CNNs in PyTorch are not too complicated. It's very similar to the multi-layer perceptrons that we implemented before. So here I'm looking, or here I implemented the Linet 5 architecture, which is the one that I showed you early in this lecture. And the init part, or the definition setup part, is very similar to what we have seen before in the multi-layer perceptrons. The interesting part happens here. This is the feature extractor part, so this would be this part. And then here I have the fully connected part, the classifier part, which is this last part here. So let's look at this feature part first. So this is the part where this receives the input, the first convolution layer receives the input image. So the number of input channels is equal to 1 or 3, depending whether it's a grayscale or a color image. And then it outputs 6 channels. And these 6 channels, they will go into the next convolution layer. But between the first convolution layer and the second convolution layer, we have first the activation function. And it's the same concept as in the multi-layer perceptron. We have nonlinear activation functions. And this could be also, for example, ReLU and all the other activation functions we've seen before. Here I'm using 10H because that's what was used in this original architecture. And then it's followed by a max pooling layer. And then after the max pooling, there's another convolution layer, another nonlinear activation function, and another max pooling layer. And the 2D comes from the fact that we work with 2D images, right? So because you could technically also apply a convolutional network to a 1D input, for example, sequence data, if you have a time series. Okay, so the output, so this will produce an output, and the output will be, if you would compute it, it would be 16 channels. So this is the 16 here, times 5 times 5. So we would have 16 of these feature maps. And this will then go into the classifier section. So the classifier expects a vector, right? So what we have to do is, so the dimensionality would be 16 times 5 times 5. What we have to do is we have to flatten the output from features. So again, in this part at the top here, I'm just defining things, and in forward, I'm actually calling them. So I'm calling the features first, which will return these feature maps. And then I'm flattening the feature maps such that they are a vector. And then this vector here is passed into the classifier. And this classifier is this part, which is just like a multi-layer perceptron. And then I'm applying the output, after the output layer, a softmax function, and then returning the logits and probabilities. And this is just like a normal multi-layer perceptron. So for more details, so this is actually all we need to know, but if you want to see the remaining code, if you want to see this applied to MNIST and the Cypher 10 dataset, I made some notebooks here, so you can execute them if you like. Also, if you like, I actually implemented a cats and dogs classifier. Here I'm using the VGG16 architecture. We will talk more about the VGG16 architecture next lecture, but also if you're interested, you can check out this code. Yeah, one fun thing you can do with these CNNs is to look at what parts of the image it pays most attention to. So one of the techniques, there are many more, is called guided backpropagation. And this is maybe the most intuitive technique. How that works is simply that you compute so you compute the gradient, but instead of with respect to the weights, you compute the gradient of the loss with respect to the input pixels, the x's here. And also what you do in addition to that is you clamp all the negative gradients during backpropagation to 0. So that will give you then the gradients that are positively correlated with the loss, or the loss with respect also to the class that you're looking at. You do this with respect to the class, of course, because when you compute the loss, you give it the class label. So what you can see here, and this is maybe not a good example, but I just had this cats and dogs network trained, so I applied this here. So you can see it pays most attention to the legs, actually, the legs of the cats and dogs. If you want to play more around with this code example, or you want to use it for your projects, I implemented and uploaded it here. So if you would like to play around with this, I made a folder inside the code folder with this code to generate these. And with that, let me end the lecture. One more thing is the reading material. So I made the lecture without looking at any reading material, so there is no good resources I can recommend. I was searching online for something that might be useful to you. So in the deep learning book that I mentioned before, there is a convolutional neural network chapter which you may find helpful, but again there may not be much overlap with the lecture I talked about, except that of course all the fundamental concepts are the same. But if you have any questions, please ask me. We have an office hour today, so please ask me during office hours, and also you can always ask me questions on our discussion forum. And with that, one last thing. So Jan LeCun is on Twitter. It's of course useful to follow him if you want to stay up to date with deep learning, but then there's also this nice, fun satire account, Bored Jan LeCun, which I really recommend if you, during these rather sad times, if you want to get something to laugh about. So with that, then see you at the office hours later.